So you can do a little example. And so it's just this balance of half of them having one friend, half of them having three friends, and we can do this same calculation again. This is not like the Edish-Redding ones. We need both of these pieces, right? So we need to use our two equations, the first derivative of the generating function for pi and the first derivative of the generating function for rho. We computed all of these things before, so we're not going to do it all again, right? We had these results. I mean, this is the first things we put down for this, right? This is just the p sub k generating function, right? So there's half a chance that you have a degree 1 node, half a chance you have a degree 3 node. That's just random selection. This is if you follow a random edge, and there's a quarter of a chance that you hit a node that has no other friends because it has only one total, and there's a 3/4 chance that you hit one that has two other friends. 3 ways to get to a degree 3 node. So we can differentiate all these things and play around with them because we're going to stick them into, we'll definitely need this one. And we determined this quantity before, f rho of 1, right? This is the fraction of nodes. That fraction of edges, sorry. It's a total probability that if you run along a random edge, you reach a finite component. Yeah, that's right. Good. Right, and we had that was a third. Yes. Don't have to worry about these things too much. But that's our function. We're going to stick a third in there. We're going to stick a third in there. We have these functional forms just from the previous slide, right? They're just these FRs and so on. It's going to be a simple, this guy that we're looking for is here as well, so we can just rearrange this thing. It's just a little bit of messing around. So we get 13 over 2. And then we have the other equation, so this is the average, right? The average component size, first derivative of the component size distribution's generating function, evaluated at 1. We can stick these things in, so there's a 13 over 2 coming from here, and then these pieces are just the generating function for the degree distribution. This is just some calculations, blah, blah, blah. So we get this, 122 over 27. So these numbers, these wonderful numbers, odd things, but this is, if we randomly select a node in a finite component, this is the typical size of that component. Exciting, right? So, it's a bit more than 4. So they're pretty small, actually, right? So you've got these little small isolated ones. And what that means, that makes sense. So you're going to have a lot of these little 3s with 1s ending on them, right? So you've got a node that has 3 friends, and then they're capped. All of those nodes just have the 1 friend. So all these little, I want to say triangles, so that's not right. These little structures like that, right? Middle bit of a peace sign. So, but now and then you might get something slightly more elaborate, but it's unlikely, but you're going to have, a node that has 3 friends and another node that has 3 friends, and then they get capped as well. Yep, from the bottom.
Is that actually friends or is that
These ones?
Yeah.
So this one is this is the core generating function because it's for p sub k. So this is the number of, that's probably you have k friends, like if you randomly choose a node. This R is the one if you randomly go along it, if you go along a random edge, basically pick a random edge, travel along a random direction. How many other friends does it have? Yeah. So this is the contagion. This is the one that's about spreading and contagion. We need this one because we do go to a network and go boink and see what happens because we're humans. What happens if I infect this one? The shift like that? Yeah. So right. It's the derivative of this one. This guy is the derivative of this one divided by that same derivative evaluated at 1. which is the average degree. So the average degree for this is 2, right? Because you've got an even balance of 1s and 3s, so the average degree is 2. So differentiate this, you're going to get x to the 0, and then you're going to get 3 halves, and then divide the whole thing by 2. I know, it's madness. But that's right, that's right. So these have a really, these two have this nice simple connection. It's a big soup when we're trying to get to, things get a little soupy. Yeah. All right. I want you to escape out of this section, not too much harm. So we get this, the 13/12, 13 over 2, so that's the typical size if you're running along an edge. That's a typical finite component that you reach. Good. But it's all doable, right? Okay, so that's, we'll put that in a little box.